Hey everyone, this is Karthik. What's up? So in this video we'll be solving a problem based upon digit dynamic programming, and this problem comes from Codechef long challenge. The name of the problem is encoding, as you can see. It's a really nice problem, and I would say it's considerably harder than the problems we have solved till now. And this might be the last problem of the digit DP series from my side. Unless you guys really are enjoying the series and you would like me to make more videos on this topic, I will. So you can, any kind of feedback is welcome, and you can let me know in the comments whether you want more videos on digit DP, or if you think something is missing, or you want some other topic, and I'll definitely try to, respond to each and every request. So let's get started with this problem. The problem is, I would say, on the face of it, you can say that this is digit DP. How to solve it is another matter, but right after reading the problem, you will be like, okay, this looks digit DP. So you can pause the video and read the problem statement. If you don't want to read it, I'll still explain it, so no worries. So the problem says that given two numbers L and R, okay, you need to find out summation f of x where x goes from L to R. Okay, anyone who has the slightest idea of digit DP can just look at this and say, okay, this definitely looks like digit dynamic programming. How? That's another matter, but it does look like that. Okay, good. We know that we need to find out this particular value. What is f? Also, what are the constraints on L and R? So R is a number having n digits, and that n can be up to 10 power 5. So R could be as large as 10 to the power, okay, whatever this number is. I guess one more zero. Anyway, so L and R can be huge, very large, and in fact you cannot even take input as integers or longs. You have to take strings as input. These are very huge numbers. Okay, good, no worries, we'll think about that later. But what do you mean by f of x? What is this f? So if you want, you can read it, otherwise I'll just explain the same thing. It's like reading out from a PPT, doesn't matter. So let's try to find out what is f of this number 388822442. Okay, now here if you think about it, the f of this number, first of all you give the digits some position. This is position number 0, position number 1, position number 2. Basically you number these digits from right to left, and from 0 to whatever is the rightmost digit. I'll quickly number them out. Okay, now you take the number and you break it into contiguous subsequences of the same digits. So if I try breaking this number, it breaks down to this 3. Then you take as many same digits as possible and you make a group. Okay, another group is 888. 2 does not belong to this group because the digit changed over here. Now 2 because these are same digits and they can be taken up as a group. Again 4, and finally 2. Now the overall value of this is going to be 3 into 10 to the power, what is the position of this digit, that is 8, plus 8 into 10 to the power, what is the position of the leftmost 8 of this group, that is 7, plus 2 into 10 to the power, what is the position of the leftmost 2 of this group, that is 4, and similarly for 4 into 10 power 2 plus 2 into 10 power 0. So this is going to be your f of this number. If I were to take another example, let's say 222113. So the f of this number is going to be, you make the groups first. The groups are going to look something like this, and your value f of something is going to be 2 into 10 power 5 plus 1 into 10 power 2 plus 3 into 10 power 0. Hopefully this concept of f is clear. If it is not, it's explained in these 3 points. Now we need to solve this problem. Let's go to Sublime and start solving it. So obviously the brute force is straightforward. You simply iterate from L to R, and for every number you find out f of x, right? and you keep adding these values. Of course, you need to print the number modulo 10.9 plus 7, but that's the least of our concern for now. We'll just mod everything 10.9 plus 7 once we have a solution. So that's not our concern, but for now, how do you even evaluate this f of x? It's pretty simple. To evaluate this particular f for a given integer, you just iterate through that, and it can be evaluated in big O of log x time. But that is like for just one integer. Okay, you can do that for one integer x in this much time, and overall your complexity is r minus l times log of r. This is very bad because r is up to 10 to the power 10 to the power 5. Okay, good. But we have a brute force solution. How do you actually calculate this f of x in brute force? I have the code for that also. So let's just quickly look at the code itself. So if you look at this particular part here, the brute force, you take the number like 38882244, you go from right to left and you keep adding, remembering what was the previous digit, because that will help you know whether you need to add a number or not. So initialize previous digit to 10. Basically that means that previous digit is something, because there was no digit to the left, so I'm taking some invalid digit. Okay, now 3, look whether 3 is the same as the previous digit or not. If it is not, then add to your result 3 into 10 power whatever is the position of this number. How do you calculate that position? Simple maths. You can do that on pen and paper, but for now it's going to be 0 1 2 3 4 5 6 7. Okay, next, now previous digit becomes 3 and you come to 8. 8 is not the same as the previous digit, so you add 8 into 10 power 6, and now previous digit becomes 8. You go to the right, you see 8. 8 is the same as the previous digit, so you do not add anything. Again you go here, 8 is the same as the previous digit, so you do not add anything. You go to 2. Now previous digit is 8. Since 2 is not the same as the previous digit, so you will be adding 2 into 10 power 0 1 2 3 and so on. Okay, now at this 4 you will have something that is different from the previous digit, and you will be like, okay, 4 into 10 power 0 1. For the last 4 you would not be adding anything, because this 4 is the same as the previous digit, so nothing to be added. And for this number the f value will be this thing, and you will return the result, of course after modding it, but that's not our concern right now. So hopefully this brute force thing is clear. You can just execute this function for every number from L to R and you will be done. Cool. Let's go back. Now we'll be solving it the trivial way. Okay, instead of finding the answer from L to R, I will find out the answer for 0 to R and for 0 to L minus 1, and then we'll use these two answers. However, there is one problem here. L is a very large number that I'll be taking input as a string. Okay, first of all, this is the answer for 0 to R, and this is the answer for 0 to L. I want this portion. Okay, so I could take this portion from 0 to R and remove this portion, but the problem here is that L will be taken input as a string by me, because L does not fit into the bounds for even long, right? It's much huge. So doing L minus 1 is L minus minus will be hard for me, because I'll have to write a function that can do subtraction over strings. I don't want to do that. So what I'll do is I'll take the answer from 0 to R, I'll remove the answer from 0 to L from this, I'll remove this portion. Now the only thing that extra that I removed was this L. I wanted the answer for L to be included also, right? So I'll just brute force for L and I'll include it. Brute force function, that's why it was there. The only reason for that brute force function to be there was that I need to find out what is the value of f of L using brute force. Since I'll be excluding from 0 to L, but I wanted to exclude from 0 to L minus 1. That's why I have to add this f of L using brute force. So good till here. Now just let's see how do you solve for this, and we're done. Now I'm trying to find out the answer from 0 to r, and I know that r has n number of digits, right? So basically I'm trying to find out the value of f of x for all x having n digits so that x is less than equal to r, right? So let's have this. R has n number of digits. Here you can see that n equal to 6, but n can be anything, right? This is your number r. You are thinking about all 6-digit numbers, and 0 is also a 6-digit number because we are allowing leading 0. We are allowed to have leading zeros, so 0 is also a 6-digit number. Cool. And we are thinking about, okay, how do you find this f of x for all 6-digit numbers so that x is less than equal to r? Cool. Now I'll think about generating a number, and we'll apply some dynamic programming while generating this number here. So I'm going to generate this number from left to right, and since it has 6 digits, so I'm good with the number of digits here. So at the leftmost position, I can either have a 0 or a 1 or a 2 and so on. I'm going to place some digit here. So let's say I place a digit dig here, or maybe I place the digit small x over here. Okay, cool. This small x is going to contribute x times 10 to the power n minus 1 to my total, where n is the number of digits in the number. So for this particular number, it's going to contribute to my total x into 10 to the power 5 for this for n equal to 6. Okay, good. This contribution is cool for a particular number that starts with x. Now there might be many numbers that start with x. Of course, there can be a lot of numbers that start with x. So any valid number that starts with a x, has 6 digits and is less than equal to r is going to contribute x into 10 to the power n minus 1 to the total. How many such numbers are there? Let's say there are cx such numbers. So this is the contribution we get to the total for any number that starts with an x and has exactly n number of digits and is less than equal to r. We're going to get this overall contribution. For each number we are getting this contribution because x is here, and there are cx such numbers. Cx basically represents the count of numbers that start with an x, have exactly 6 digits and are less than equal to r. This is what cx represents, and this is going to the contribution you make to the total. Good, we are good with that. So once this contribution has been made, we need to think about the remaining n minus 1 digits or 5 digits. We're good that, okay, this contribution for these cx numbers, we have taken the entire contribution for this leftmost digit, but what about the remaining digits? We need to think about that also. So before we go to that, let's define dp. So I'm going to define my dp of, basically my dp state as dp of n and some other parameters which we'll think of. So this is going to be what is the sum of fx for all x having n digits. Okay, this is good. This is the sum of fx for all x having n digits, but we need to make sure that we do not generate a number that is greater than equal to r. For that we are going to have a type variable. Okay, this ensures that we do not generate any number greater than r, or that means we stay less than equal to r. So we are happy with this. Let's see whether we can come up with a transition with only these two parameters. So when I'm trying to generate a n digit number, we saw, okay, I'll be placing an x here and I'll get a contribution c times x into x times 10 power n minus 1. We saw this. Okay, this contribution is obvious to the total. And now we'll be solving the same problem for n minus 1 digits. That's good. Now think about it. At this particular digit, whatever I add is going to give me a contribution of, let's say I put in a digit y here. It's going to contribute to the total y into 10 to the power n minus 2. Right. And then we are going to see how many numbers exist that have this digit y, this digit x. Basically, what is the overall contribution? How many such numbers are there? And we're going to add that to the total. We're always going to do this thing for y, this contribution, unless y equal to x. So if I put in a x at this position, you will see that no contribution will be made. Why? Because for a group, this will form a group like this, xx, right? For any numbers having two consecutive x together, such a group will be formed, and contribution will be taken only from the leftmost or the most significant digit of that particular group. For this, the contribution is already taken, and for this, no contribution is to be done, right? So this means I need to remember what the previous digit was to be sure that I do not make a contribution for this digit if this is equal to the previous digit. So I need to remember what was the previous digit. Okay, I figured out another parameter that needs to be there in my DP state, because this helps me remember that what was the previous digit and whether for the current digit do I need to make a contribution or not. Prev. Okay, now I have this DP state, and this represents what is the sum of fx for all x having n digits less than equal to r, given that no contribution will be made. No contribution will be made if I place the digit prev as the most significant digit of the remaining number. Okay, that's what it represents, as the most significant digit of the remaining number or of the remaining n digits. Okay, so it's basically like if I place a 8 at this position and I try to find out what is the contribution by these digits, and I place in an 8 here, this 8 should not contribute anything to the total. But if I place anything other than 8, 7, 6, 5, so anything, then it's basically the same problem for n minus 1 digits, and the previous is 8, so 7 makes a contribution good. It's basically remembering whether this digit is same as the previous digit or not, and whether some contribution should be given or not. That's it. We have a DP state now. Now we'll be going to the solution. Let's take an r equal to 7, 8, 3, 6, 2. Any number, right? Here it has 5 digits. It could have any number of digits, and it could be any number in fact. Let's see how we can come up with the recurrence. Overall, we are trying to come up with dp of n, the sum of all n digit numbers, the sum of fx for all n digit numbers, where n for this is 5, so that they are less than equal to r. Currently, there is a possibility that I might exceed r by putting a 8 at the leftmost position or something like that, right? So I need to make sure that I do not exceed r. And how about previous digit? Previous digit basically tells me whether for a particular digit that I place at the most significant digit of these n digits that I have, should a contribution be made or not. So no matter what digit I place over here, a contribution will definitely be made because it is the most significant digit, right? So I can take the previous digit to be something that is not valid, like -1, 10, 12, because these are the digits that do not even exist. Digits are from 0 to 9. So let's say, okay, the previous digit is 10. That means that no matter what you put here, it's not going to be equal to the previous digit. You can take a -1 or anything that represents something, represents an invalid digit. So I'm taking, okay, the previous digit was 10 and I'm trying to find out the answer for this. This is the sum of fx for all n digit numbers that are less than equal to r, and any digit placed at the most significant position will make a contribution unless it is equal to 10, and 10 is obviously not a valid digit. So this is dp of n110. Now we need to come up with the recurrence. Okay, that's a lot to digest. You can rewind for maybe 10 seconds if you want, or obviously the comment section is open. So I'm going to place a digit over here. I place x, or I place a 0, I place a 1, I place something. Okay, if I place a 0 here, then the contribution would be 0 times C of 0, the count of valid numbers that are less than equal to r and have the most significant digit as 0 and have exactly n digits. This is the contribution made if I place a 0 at this position. Sorry, 0 times 10 to the power n minus 1 times C of 0. Okay, and then I'll recur for the remaining digits. And that's going to be the contribution by these digits. If I place a 0 at this position, is going to be dp of n minus 1 digits. Of course, I can never exceed r anymore because I placed a 0 at this position. This means no matter what I place at the remaining positions, I will always be less than equal to r. My number is always going to be less than equal to r. So I can say, okay, type is 0 and The previous digit is also 0. So any digit placed at this position will make a contribution except for 0. Okay, good. Hopefully this part is clear. If I place in a 1 at this position, then the contribution made would be 1 times 10 to the power n minus 1 for placing a 1 here. And how many such numbers exist? So count of numbers having exactly n digits and are less than equal to r and start with a 1 is C1 plus dp of n minus 1, and I can never exceed r again for these digits because I placed a 1 here. So I can never exceed r now. And the previous digit is obviously 1. Okay, good. Similarly, so until 6 is going to be similar to these. And finally, we'll have 7. If I place in a 7 at this position, then the contribution made is 7 into 10 power n minus 1 into C7. We'll see how to evaluate C. It's very easy. I'll just show you the code for evaluating this count. Or if you've seen my previous video, then this should not be a doubt because we had a very similar thing to this. In fact, exactly same thing. Okay. So this is the contribution made if I place 7 at this position. And what is the going to the contribution for the remaining digits? It's going to be dp of n minus 1 for sure. And there is a possibility I might exceed r in the future by placing a 9 here or something other. So it's going to be 1 for tight, and the previous digit is going to be 7. So anything placed over here will make a contribution except for 7. So if I place a 7 here, no contribution should be made. And a recurrence is ready. We're done. That's it. Let me show you the code and things will become much more clear. Hopefully you like the video. And of course, if you have any doubts, you are more than welcome to ask me in the comments. This is the entire code. I'll just zoom in and explain. Yep. So here, I'm trying to find out all the numbers having exactly n digits which are less than equal to r. The previous digit is given by this variable, and the tight, whether I can exceed r in the future or not, is given by this variable tight. If there is no digit in the number, that means 0 digit numbers or empty number, then of course f of an empty number is going to be 0, so I just return a 0. So hopefully base case is simple. Next up, if I've already solved the sub problem, then do not calculate the answer for the sub problem again and just simply return it. Good with this. Next up, okay, initialize answer to 0. Now we are actually going to do some calculation. Give me a second. Yep, it's recording. Just wanted to be sure. Yeah. So the answer is 0. Good. Now we're going to do some calculation. So if tight is 0, let's say r was equal to 7, 8, 3, 6, 2, and I'm thinking about these 3 digits right now. Okay, for example's sake, n equal to 3, and I'm thinking about these 3 digits. These 2 digits are already placed, so I'm not thinking about them. Now tight can either be 0 or 1. Tight can be 1 if these 2 digits are 7 and 8. Otherwise tight is going to be a 0. If tight is 0, I can place any digit at this position from 0 to 9. Okay, and if tight is 1, that means this was 7 and 8, then the only digits I can place at this position is going to be 0, 1, 2 or 3. If I place anything greater than 3, then I exceed r, which I do not want. Okay, good. So if tight is 0, if tight is 1, then I'm bound by this corresponding digit of r, that is 3. And if tight is 0, then I can go up to 9. This is the upper bound that I can place at this position. Okay. So now I can place any digit starting from 0 and up to ub at this position or upper bound. Okay, I'll start putting these positions one by one. Okay, putting these digits one by one, and I'll see if digit is not equal to the previous digit, which is given by this variable, of course, then some contribution will be made, that is given by this ll contri term. Some contribution will be made if digit is not equal to the previous digit. For example, if I put in 5 here and the previous digit was maybe 2, then a contribution is going to be made which is equal to 5 into 10 power 0, 1, 2, that is n minus 1, right? Because n equal to 3 and n minus 1 equal to 2, so it's going to be power of n minus 1. Sorry, right? 5 times power of n minus 1, that is 5 into 10 power 2. If I place 5 here, into how many numbers exist that have a 5 here, Tight is 0 and you have two numbers. Okay, how many such numbers exist? You find it using the CNT function. You can look at the code for that, but it's fairly simple. Since tight is 0 and you have 2 digits to place, you can put 10 digits here and 10 digits here, 10 cross 2. So it's obviously 10 power 2 for that also. But let's just say C of 2-digit numbers. How many 2-digit numbers exist given that tight is 0, right? So you need to think about these 2 digits. But tight is 0, so you can place literally any numbers at these two positions. So it's count of 2-digit numbers so that you do not have to think about R. This is the contribution made if I place a 5 at this position, and if the previous digit was 2, this is a contribution that will be made. That's good. Contribution is cool. And then you add it to the answer, the contribution, and you think about the remaining 2 digits. How do you find the answer for the remaining two digits? It's going to be dp of n minus 1, that is 2, comma, tight is 0, previous digit is 5. So basically any digit placed here will make a contribution except for 5. So previous digit is 5 and tight is obviously 0, right? So this also you need to add to the answer, and this is exactly what we're doing. Yep. So this will solve for the remaining n minus 1 digits. You pass in what is the digit you placed at this current position. I placed 5, so I pass in pass a 5. Tight remains 1 if tight was 1 and the digit that I placed at this position was equal to the upper bound. Otherwise tight becomes 0. So the only case when tight remains 1 is that tight was already 1 and the digit that I place at this particular position is equal to the upper bound. That is the only case when tight stays 1. Otherwise tight becomes 0, right? And I find out the answer for that and I add it to the answer. Finally, once I'm done calculating the answer, I return it after modding with mod. That's as simple as that. If you have any doubt, let me know in the comments, and I guess we're done with the video. Let me just show you the CNT function also. It's fairly simple. Also, this is the DP table. Yep. This function is used to find out the count of numbers that has exactly n digits, and given the tight condition, tight, okay. So if any and let's say r equal to 78362, and let's say n equal to maybe 2. So this means I'm trying to find out how many 2-digit numbers are there, keeping in mind that I should never exceed r. Okay, so if tight equal to 0, this means no matter what digits I place here, you can never exceed r. So having 2 digits, you can place 10 possible options for here, this position, 10 possible options here. So it's going to be basically 10 power 2. Sorry. So power 10, 2. 10 to the power, the number of digits you have, if tight is 0. Cool. If n equal to 0, then you return 1. What does that mean? So if you do not have any digit to place, you will ever, the only time when you reach here is that tight equal to 1 and n equal to 0. This means that the number you generated is exactly equal to r. That means you have exhausted all the digits, no more digit left to place, and this is one valid digit, the r that you just created. Tight remained 1, so you return a 1 for that. For r equal to 7, for the number you generate 78362, that is one valid number, and this is the only case when you reach here. Okay, if you have already found out the answer for this particular sub problem, then you return it. Otherwise, you think about it. You see that, okay, 78362, r equal to 78362. The number you want to generate is 2-digit number, but tight equals to 1. That means obviously the previous digits you placed were 7, 8, and 3. That is the only case when tight equals to 1. Now you want to find out, okay, how many such numbers exist which are going to be 2-digit long and you do not exceed r. So for this position, you can place any number from 0 to 6 represented by ub. You place in a 0 here, and then you will be like, okay, how many 1-digit numbers exist such that tight is 0? That is 10 power 1. Similarly, if you put in a 1 here, you will be questioning the same thing, 2, so until 6. If you place in a 6 here, you will be like, okay, how many 1-digit number exist so that tight equal to 1? That means you need to think, you need to generate a 1-digit number while taking care of what is the corresponding digit of r. And this is a recursive thing. Very easy to write out. Hopefully guys you liked the video and solution is clear to you. If you have any doubts, you can let me know in the comments. You have to subscribe to the video and you have to like the video. And I'll see you in the next video. Bye bye.